We're going to start working on distance. Well, we've had distance between 2 points, right? Pythagorean theorem, delta x squared plus delta y squared plus delta z squared. Take the square root of that. But now we're going to talk about more interesting situations. So if we're going to start off with an intro to distance, and I hope this makes it all make more sense. So let's draw, we're talking about distance to a line or a plane. So here we go. Here is a line. Okay. And then we want to know how far away this point is right here. We'll call it P1. So this is any point. Could be by itself. It could be on a line or on a plane. Okay. And we have a line or plane, 2 space or 3. Of course, planes in 3 space. So we want P1, how far away it is. Well, distance, when people talk about distance between things, they talk about the shortest distance. Not the wrong way around the whole world or something, but the shortest distance. So that means the perpendicular distance right there. Okay. So that is the distance we're looking for, D. Okay, that's what we're looking for. The lines don't mean anything. It's just to emphasize it. All right. And we're going to dress this up a little bit now. So what do I mean by that? Well, we have on our line or plane, we have P naught. We have a direction vector for the line or plane, U. Okay. We have the normal, right, to the line or the plane. And I'm going to add one more thing in here. And I use the line tool. And I just made it into a right triangle. Okay. And if we know what P naught and P1 are, if we have the coordinates, the position for P naught and P1, then we can get the distance of the vector from P naught to P1 as well. And let me see. I guess that's not bad to start with. So just make a note, the shortest distance is always perpendicular to the line or plane, right? So there we go. Because we have a right triangle, we can use SOHCAHTOA to find D. Right. Now, if we have the angle between the normal and P naught, P1, theta, if we have that angle, right, just to, if we have that angle, then we can use what to get D? Well, it's a cosine. So cosine theta is D over P naught P1 magnitude, right? And D, solving for D, we have P naught P1 cos theta. Now, this should really be familiar to you because it's part of what? Well, by definition of dot product, with a definition, by definition, P naught to P1 dotted with the normal is P naught P1 magnitude, normal's magnitude, cos theta. And notice we have 2 parts the same, right, is what we want there. So that means if we divide both sides by distance, by magnitude of the normal, you get P naught P1 magnitude cos theta. So distance, the dot product from P naught to P1 with the normal divided by the magnitude of the normal. Okay, and you go, okay, great. Well, there's a formula. So it's dot product if you have the normal, P naught to P1 dotted with the normal. If you have the normal, so when can you use this? Well, need to have the point, obviously, otherwise you can't even start. It isn't even a question. But you need to have the normal. So what situations do you have the normal? Well, obviously a plane and in 3 space. Of course, the plane's in 3 space. A line, do you have a normal to the line? Yes, but only in 2 space. And you have the normal if you have skew lines. What do you mean? Well, you can have the normal. You get the normal by crossing U1 with U2. That's perpendicular to both of the skew lines, and that'll be the shortest distance that the 2 lines get to each other. And then, you'll be able to use cosine. All right. Well, what if we don't have the normal? What then? Well, then you need to have some other information about the direction of the vector, so of the plane or the line you're finding the distance to. So we'll call that alpha. And sine alpha is distance over P naught P1. And maybe you can guess where we're going with this. Sine is part of dot product, right? But before we get there, we'll solve this for D. Oh, P naught P1. Put the magnitude first. And then by definition, the magnitude of P naught P1 crossed with the direction vector U is magnitude of P naught P1 U sine alpha so we can divide both sides by U, magnitude of U. So we get P naught P1 crossed with U divided by the magnitude of U, leaving P naught P1's magnitude sine of alpha. And so distance is P naught P1 times the magnitude of U over U. Now, when do you have the direction variant? Well, if you have parallel lines in 2 space or 3, and if you just have a point, you're finding the distance from a point to a line in R2 or R3, depending which equation of the line you have. If you have the Cartesian equation of the line in 2 space, then you might as well use the other formula. But here are the key formulas. All right. Now, okay. I'm going to go on to the note for 9.5 now. And it looks like I'm out of order, but that's okay. It doesn't matter. Find the distance between point 1, 3, -1, and the line. Okay, so this is a line in 2 space. We have the normal. The normal is -2 and 3. We need a point on the line, so we need a P naught. Looks like we have, I don't know, 3 and 0, an x-intercept. 3 and 0, I just picked any point off the line. So the distance will be P naught P1 dotted with the normal over the magnitude of the normal. So we're going to do, I have to get P naught P1 is 3 minus 3, which is 0. Nice. And -1 minus 0, so -1. So we're going to dot 0 and -1 dotted with -2 and 3 over the magnitude of the normal. So -2 squared plus 3 squared. So I get -3 over 13. I guess one thing I didn't say, it can't be negative, so it's the absolute value of that. So this is 3 root 13 over 13 rationalized. There's the distance. Okay, they have a more complicated formula. I guess you can use it, but I never seem to want to remember it. Here they're giving the other formula that we had, right? The formulas we did in the introduction are here. I mean, it's not like I'm not using them, but I'm not using the special ones they're giving. For each case, find the distance from the given point to the line. Okay, this time we don't have the normal, we have the direction vector. So the distance formula we're going to use is the one involving cross product. So P naught P1 crossed with the crossed with the direction vector over the magnitude of the direction vector. There we go. This is P naught. This is U. So I need to get P naught P1. I have 1, 1, and negative 3. So, I'm not going to go through how to do the cross product. I hope that you know how to do the cross product at this point. But we're going to cross them. It doesn't matter which order you cross them in, but to be consistent, P naught P1 should be first. But we get 6, 3, 3. The magnitude of U, which is 1, U is 1 squared plus 2 squared plus 0 squared. So we get magnitude of 18 plus 36, 54 over the magnitude of 5. 270 over 5. There we go. And this one here, we need the distance. We have the direction vector, of course, and the origin. So that's P1. The direction vector is 2, negative 3, 0. P naught is negative 1, 0, and 2. P naught to P1 is then 1, 0, negative 2. Distance will be P naught to P1 crossed with U. Magnitude over the magnitude of U. The cross product we have here is negative 6, negative 4, negative 3. Magnitude of U is root of 14. Oh, we're doing magnitude on the top still. It's 36 plus 16, 52, 61. Root of 61 over, not 14, root 13. Root of 13. Oh, rationalizing that. 793, root of 793 over 13. It's example 2. Example 3. Find the distance between parallel lines. So notice that these normals are the same. So we do have the normal. So it'll be P naught to P1 crossed with the normal. Dotted with the normal over the magnitude of the normal. I guess I'm going to use line 1 is P naught, and I'm going to use 3 and 0. I'm going to use 0 and 2, like that. And the normal from that is 2 and negative 3. And from the other one, I'm going to get P1. And P1 I'm going to use is, oh my goodness, I don't want to use a fraction. I don't know. Wow. Okay. 19. No, that's not going to work. Oh, heck with it. I'm going to use a fraction. 0.5. So P naught to P1 is 0 and -3/2. So 0 and -3/2 dotted with 2 and -3 is 9/4. Magnitude of n is the root of 4 plus 9, root of 13. So we have 9/4 over the root of 13, which is the same as 9 over 52 times the root of 13 times the root of 13, and that does not reduce. All right, so we need the point that's closest, not the distance. They're calling it the foot. So the foot is some point on the line. So some generic point on the line is this, and I'm just using the parametrics. So if you tell me t, I can find any point on the line. And what we have to do is make it so that from this point to the foot, so what's that vector? So we're going to be subtracting OF and OP, -5 plus t, 7 minus 3t, and -1 plus 2t. This point to this generic foot point, well, the foot point we're interested in, if it's the right point, then that'll be perpendicular to the direction of the line, and the dot product will be 0. So what we have to do is find t so that this equation is true. And the direction vector, of course, from the line is 1, -3, and 2 is equal to 0. Now you just have to be careful of your integers so that things will work out. -5 plus t minus 21 plus 9t minus 2 plus 4t is equal to 0. I have 14t minus 28. Yeah, so t is equal to 0. And our foot point f will be at -2, not 0, it'll be 2. So our foot point will be at 0, -3, and 5. So there's our foot point. Find the equation of the perpendicular line from the point to the line. Okay, it doesn't say the form of the equation. Okay, we'll just well, the normal is actually the PF. So I'm going to plug in t is equal to 2 into that, and I get -3, 1, and 3. And you can verify that the dot product will be 0 if you do that. And yes, it is. So I need the equation for a line from the point P. The point P was 3, -4, and 2, plus S, not T, use something else. And the normal is the direction of the perpendicular line. There we go. Find the distance from P to the line. Well, that's just the magnitude of PF. Okay, so that's the magnitude of -3, 1, and 3. And that'll be the root of 19. Okay, find the shortest distance between two lines. So they are lines in 3 space. They are not parallel. So if the distance is 0, then they intersect. If the distance is not 0, then, they're skew lines because we know they're not parallel, right? So distance is P naught to P1 crossed with the direction vector. Oh, no, dotted with the normal. We don't have the normal. We'll have to get the normal over the magnitude of the normal and magnitude. The normal is simply the cross product of the two direction vectors. So we'll have to do that. It's 1, 1, 0, 1, 1, 0, 0, -1, 2, 0, -1, and 2. just going through the cross product algorithm. It's 2 minus 0, 0 minus 2, right? And then finally negative 1 minus 0, so negative 1. So it is P naught to P1. So we're going to take this to be P naught and this to be P1. So P naught to P1 is negative 1, 1, and 1. So we see the magnitude of negative 1, 1, and 1 dotted with 2, negative 2, and negative 1 over the magnitude of the normal, which is 2 squared plus negative 2 squared plus 1 squared. So that is root of 9, which is 3 on the bottom. You have negative 2 minus 1 magnitude, so that's 5/3. The distance between these two skew lines is 5/3. Okay, going to roll right into 9.6. This is still one of the formulas we had before. If you're given the normal, use dot product. I just used it in the last example. If you just find the distance from a plane to the point, we can get a normal. So that's the first step here. The normal, we'll call this direction vector u, and this direction vector v. We'll call this P naught, and this is P1. So distance is P naught to P1 dotted with the normal. Magnitude of that over the magnitude of the normal. So the normal first. Well, we have a few things to do. Since I have it right here, P naught and P1 first, I guess. So we have 1, 3, and negative 2. The normal will be u crossed with v, and you should know the algorithm by now. It is 1 gives 1, 4, and negative 2. Okay, I'm going to do all the work on the side here. How about that, eh? Dotted with the normal, I have 1 plus 12 plus 4, 17. And the magnitude of the normal, it'll be 1 plus 16 is 17, root of 21. So I have 17 over the root of 21, or 17 root 21 over 21. This is the parametrics of a plane. So we'll just go through this. Let me see the two direction vectors. We'll call P naught 1, 2, negative 1. U is the coefficients of T. We'll do that. And V, the coefficients of S. So there we go. We'll call this P1. So P naught to P1 is 0, negative 2, negative 1. The normal is u crossed with v. So the u vector crossed with the v vector. And when you do that, you get 7, negative 1, and 3. So P naught to P1 dotted with the normal. We'll dot these. 0 plus 2 minus 3, negative 1. And the magnitude of the normal is 7 squared plus 1 squared plus 3 squared. So that's 59, root of 59. So distance, which is P naught P1 dotted with the normal, over the magnitude of the normal, is going to be 1 over the root of 59, rationalized as root of 59 over 59. Find the distance from the point to the plane. So this time we have the normal. So when we have the normal, we dot it. So P naught to P1 dotted with the normal, the magnitude of the normal. We need a point. So we'll call this P1. P naught is some point on this plane. We'll do 3, 0, 0. And of course, the normal is 2, negative 3, and 1. P naught to P1 is negative 2 minus 3, negative 5, 0, and 3. P naught dotted with P1 is negative 10 plus 0 plus 3 is negative 7. Magnitude of the normal, 4 plus 9, 13, root of 14. So this is 7 over the root of 14, which ends up being root of 14 over 2. There's the distance. Find the distance between the parallel lines. So we have parallel planes, so we have the normal. So the normal we'll use, we'll reduce it. We don't need to use, we just need the right proportion. So it's 1, 2, and negative 3. That's what we'll use as a normal. P naught's from this plane, so we'll use 1, 0, 0. P1 is from this plane, and so we'll use 2, 0, 0. P naught to P1 then is simply 1, 0, 0. P naught to P1 dotted with the normal is just 1. The magnitude of the normal is root of 14. So distance, what the plan is, P naught to P1 dotted with the normal over the magnitude of the normal is 1 over root 14, or root of 14 over 14. Okay, we're almost done. Oops. Example 4 we are not going to do. So it's just example 5. Consider the plane given and the point given. Find the vector of the line that passes through the point P and is perpendicular to the plane. So the line's going to be perpendicular to the plane. So the direction vector for the line is the normal of the plane, and it's got to go through that point. So R naught goes to P, so 2, 3, and 0, plus T, and the normal is negative 1, 2, and negative 3. Simple as that. Find the point of intersection between the perpendicular line and the plane. So the way to do this is to plug in the parametrics. So we'll call this the line. Then for the line, just looking at the parametrics, we have for the x, we have 2 minus t. For the y, we have 3 plus 2t. For the z, we have negative 3t. We're going to plug those into the plane and solve for t, and we'll find the point of intersection. So let's do that. We have negative x, so negative 2 minus t plus 2y, so 2 times 3 plus 2t, minus 3z, so negative 3t plus 10 is equal to 0. Negative 2 plus t plus 6 plus 4t plus 9t plus 10 is equal to 0. 14t plus 14 is equal to 0. So t is equal to negative 1. So we're just going to plug that into the line, and we get, so what I mean is I'm going to plug it into this equation of the line. For t is negative 1, and we have to work through this. So we end up with 3, 1, and negative 3. So, there's a negative here, so that's positive. Okay, so the point, the foot point is at 3, 1, and 3. Find the shortest distance of the point. Well, of course, that's just from the distance from the point to F. And since we know both those, we're just finding the distance of 1, negative 2, and 3, which one more time is the root of 14. That's it for distance.